Hello everyone. In today's lecture, we'll be continuing with star and delta transformations, and we'll also try and start with series and parallel connections. Okay, so there's nothing other than this topic. Like this is something that would be new for you. Star and delta transformations is something new to you. Series and parallel we've been doing so far even in our questions. But I need you to understand what are equipotential nodes and how to solve questions based on equipotential nodes. So we'll again take series and parallel connections in detail for today. Okay. Also, I need you to understand, we'll try and also cover voltage division principle and current division principle in series and parallel connections respectively, and I want you to understand how to solve questions based on division principle. Okay, so let's begin. Okay, so in star and delta transformation, see, first thing you need to be clear about is the formation. Okay, so what is a star transform? What is a star? Tell me, what is a? I think I've made some mistake. Just give me a second, okay? Uh, a star is this, right? Right? A star is this. This is a star formation, right? This is a star formation. Now, no, there's no mistake. Okay. Now I want to convert this thing into what? Into a delta form. Why is such transformation required? You'll know when you solve questions. There are questions in which you get stuck, and there's no way out to solve the questions in a way that you can eventually lead to a series parallel connection. So in such questions where you encounter a star formation and you have to convert it to a delta, you are encountered with a star and you have to convert it to a delta. What is the formula? The formula is Z1 ZA plus ZB plus ZA ZB into Z3. This will give you what? Z1. See, I am repeating it for you. The impedance between two nodes A and B is calculated. Tell me how it is calculated. It is calculated by summing up the impedance here plus here, then also adding ZA plus ZB divided by what? ZC. Okay, so what will it give you? The impedance between ZA and B. Am I clear? Okay. This is Z2 for you. Okay. Similarly, for delta to star transformation, so what is delta? Delta is this triangle is delta. Okay. So if I have to calculate what? I have to calculate ZA, right? If I have to calculate ZA, this should be Z3, I'm sorry. This should be Z3. Okay. If I have to calculate ZA, what will I write? ZA, Z1, Z3 divided by what? Z1 plus Z2 plus Z3. Right? If I have to calculate this, I have to multiply this and this divided by sum of all impedances. This will give us what? Delta to star transformation. Okay. So these are basic formulas to solve star and delta questions. In general, star to delta conversion of a star network. When you are converting a star network to an equivalent delta with identical elements, star to delta conversion of star network with identical elements increases the impedance by 3 times in a corresponding delta connection and vice versa. I'll tell you how. See, let us assume the impedance to be what? Let us assume the impedance to at the impedance of star network to be say 3 ohms. It is just an example, okay? I am assuming it to be what? 3 ohms each, right? It is identical impedance, right? Tell me what will be its delta. What would I find Z1 to be? Z1 would be what? 3 plus 3, right? Plus 3 into 3 divided by 3 is equals to what? 9 ohms. Can I say it is 3 times the impedance of star? I was provided with identical star network elements. Then the equivalent delta impedance was found out to be what? 3 times the star impedance, right? Right. Similarly, now let us calculate delta to star transformation. This time I am telling you, let us take rather than 3, let's take the impedance to be 4. Okay. Let us take the impedance to be what? Let us take the identical delta elements to be what? 4 ohms. Right? If each of them is 4 ohms, now we are calculating what? Equivalent star. Yeah. That means we are calculating this value. Let us calculate this. So it will be ZA is equals to what? 4 into 4 divided by 4 plus 4 is equals to what? It would be 4 into 4 upon 3 into 4. Can I say this? Can I write it is 1 by 3 times of the delta impedance? Okay, right? Can I say it? Can I say it? Right? So, in general, I'm giving you a statement. Tell me if it's true or not. In general, tell me if I write, would I be correct? Star to delta conversion of a star network with identical elements increases it's not increases, rather with identical elements. The star to delta conversion of a star network with identical elements to equivalent delta network will result in delta impedance equal to 3 times the star impedance value. Tell me if this statement is true or not. Tell me if it's true. The star to delta conversion of a star network with identical elements to equivalent delta network. What are we doing? We are converting a star network to what? Equivalent delta network. it will result in a delta impedance equal to what? 3 times the star impedance. The statement is true, right? Remember this as a fact. Why? Because in your questions, particularly in BARC and in case you're fighting for PSUs also, you'll find questions directly of this type. Okay, and even in your if you have research entrance exams, you'll have questions directly coming on fact based questions. So in questions in BARC and PSUs, you'll find direct fact based questions, and in such questions it's very important to on also in general also, in order to increase your speed you need to remember the facts by heart. Okay, so remember this fact by heart. If you're converting from star to delta, you're given with identical elements and you have to convert it into an equivalent delta. It will be what? 3 times the star value. Am I clear? Similarly, can you write the vice versa statement? Okay, so I'm moving on to next slide. Okay, can you write the okay. Okay, solve this question for me. And before you solve this question, rather you tell me what is the impedance for in case of capacitors. What is the impedance in case of capacitors? Can I write impedance in case of capacitor Z is equals to what? 1 upon j omega c. Can I write that? Right? Right? Now tell me, this is one thing before solving the question, this is one thing that you should be what? Aware of. I hope we all know this. Right? Second thing, tell me what are you provided with? Is it a star connection or is it a delta connection? Tell me, is it a star connection or a delta connection? See, this is a star connection. Star connection is any point in network. If you find a neutral point N, such a network, rather a common point N, then such a connection would be what? Star network. Okay? Okay? So what are we intending to do? Tell me, what are we intending to do? We are doing what? Star to delta. Now tell me what we have done in this question, in this statement. Can we apply it directly here? No. Why no? You are not provided with what? Identical elements. These are not identical. These are what? If one of them is given as 1 farad, the other is 2 farad, the other is 3 farad. Please remember, these are the capacitance you are provided with. These are not the impedances. These are what? Capacitances. These are not impedances. And the formula that you have for star to delta conversion. See, the formula that you have for star to delta transformation is what? It is for impedances. It is not given for your, I'm pasting it here. Okay. So this is what our formula is, and this is what we need to use, right? Now, seeing this, can you solve your question? It's a very easy question. All I need you to be very, next time that you see a question based on star and delta, you should be very, quick in solving such questions. These questions should not take your time. These are not supposed to take your time, right? So tell me, let us consider this impedance. Let us consider what? This impedance. I'm telling you to consider what? This one. Okay. CA. Tell me what is the impedance corresponding to CA. Can I write it to be 1 upon j omega CA? Can I write it to be this? Because what? We're given with formulas based on impedance, right? Right? This I'm writing, noting this one to be what? A, this one to be B, and this one to be C. Okay? Okay? Now tell me, for CA, what will I write? This plus this. So this should be 1. What is the impedance here? 1 upon j omega bracket 1 plus 1 upon j omega bracket 2 plus what should I write here? 1 upon j omega into 1 upon 2j omega. Can I write it? Right? ZA, this is ZA, this is ZB, divided by what? ZC. What is ZC? 1 upon 3j omega. Right? Also, if you don't want to make it very clumsy, you can reduce it right at this step. How can you reduce? See, this is a common factor. This is a common factor. In these two, only one j omega will survive, right? So this 1 by j omega will eventually cancel out. Solve it for yourself and you will realize what I am saying is true. I can rewrite this to be 1 upon 1 by Ca, 1 upon 1 plus 1 upon 2 plus 1 by 2 upon 1 by 3. Right? Right? So this will become 1 plus 1 by 2 plus 3 by 2, which equals 3. 1 by Ca equals, I'll rewrite it for you and I'll add a page for, so that you can view it better. Can I write Ca is equals to what? 1 by Ca is equals to 3. Ca is equals to 1 by 3. Solve for rest of the impedance yourself. Right? I'm giving you the answers. Cb is calculated to be 1 farad and C is calculated to be 1 by 2 farad. Okay? At this juncture itself, try and cancel out j omega throughout and you will realize, yes, the j omega is cancelling out throughout, right? And only because it is cancelling, you'll have, it will be less clumsy for you to solve. Okay? So it is a basic star to delta conversion. There is nothing new about this question. The only newness was brought by the fact that it is about impedance, and in capacitance the impedance is 1 upon j omega c. That was the only novelty in this question. Right? Otherwise it is a very, to the point, put the value, get the answer question. Okay? Okay, moving on. So, I told you we'll be doing series and parallel questions, parallel connections, and you guys are very familiar with the concepts of series and parallel. I don't need to repeat it for you, but now only because it is essential, I'm covering it. Why? Because uh, in network theory, it is very important to understand what are equipotential nodes, and only when you can identify what are equipotential nodes, you will realize how important it is to solve questions and how easier it makes us. See, what appears to be a very it is appearing to be what a difficult question to handle, right? I'll tell you in a few minutes how this easy question becomes a, a simpler question to solve. The question is asking what? The question is asking you to determine what I1, I2, I3, I4. Okay, so this is what the question is demanding, right? And you have to solve it in this question. Okay, so tell me, what is a series connection? Okay, two elements are said to be in series. Two elements are said to be in series if the current through the two elements would be same. Look at this figure. Look at this figure and tell me, is there any element, are there any two elements in this network? In this network, are there any two elements which are in series? No. The answer is no. There are no two, because the current, see, look at this node. Okay, this is V1. I have missed out writing it. This is V1, and this is a current dependent. This is a voltage dependent current source, and the voltage is V1, the potential across this resistor. Anyway, so if you look closely, the current in any element, the current in any element, the same. Any two elements is not the same. See, if I talk about this, a branch of current breaks here, a branch of current breaks here. Now come to this point, another current division. Come to this point, another division. So if you look closely, there are no two elements which have same current flowing. So there is no element in series in this question. Okay. What is a parallel connection? A parallel connection is two elements would be said to be are said to be in parallel if voltage across two elements would be what is what same, if the voltage across two elements is same. Okay, so tell me, do you find any two elements, just by the by one single view, can you tell me two elements which are in parallel? See, by a general look of it, you might assume that also there are no parallel elements in this network, but it is not true, and this is why it is important to understand what are equipotential loads. Okay, I am writing, I'm naming these nodes, and then I'll try and explain what I was talking about. Okay, I'm naming these nodes to be, let us name this one to be A, this to be B, C, D, E, and F, right? Now, now look closely and tell me, are A and C at the same potential? Are A and C at the same potential? Yes, they are. Why? Because they are connected by a thick conducting wire, which means they are at the same potential. Similarly, can I say C and E? C and E are what? At the same potential. Again, the concept remains same. The concept remains same. Why? Because they are at the same potential. Right? Because they are connected by a thick conducting wire. The same you can say for B, D and F. In general, in a nutshell, can I say A, C and E are what? Are equipotential. Why? Because they are eventually connect potential. Okay. Similarly, B, D and F are what? Equipotential. Right? Both of them are what? Equipotential. Can I say it? Tell me, can I say it? Right? So, in this question, you are asked to find out what? I1, I2, I3 and I4. Right? And you are provided with a network shown as such. Right? Also, I want you to identify each and every element. This is a resistor of 25 ohms. The potential across this resistor is what? V1. Right? The potential across this resistor is what? V1. Right? This is, and this is what? It is a voltage dependent current source. In yesterday's lecture, we did what are dependent sources, right? We did questions based on dependent sources. So, in this network, this is what? A voltage dependent voltage. It is 0.2 times V1. So, it is a voltage dependent current source. It is again a resistor. This is a independent current source. And this is again a resistor. See, why I'm focusing on such points here, because whenever you see a question, you need to understand each and every element. This is what? It is a current source, right? But it is dependent on the potential here, right? So what I'm doing is I'll tell you one by one and just focus on what I'm talking. Okay? Just see if this figure and this figure is equivalent. Okay? See, from whatever I've discussed so far, we did deduce that A, C and E are equipotential points, right? Similarly, we deduce B, D and F are equipotential points, right? So, I am redrawing this circuit and I want you to understand how to redraw any circuit if the points you can, if the nodes you find out to be equipotential. Okay? See, there is a resistance between A and B. Yes, there is a resistance between A and B. It is a 25 ohm resistor. There is a 25 ohm resistor. Potential taken, V1 is taken to be with plus towards the A side. Yes, I did draw it. Right? So, is there any confusion till now? No. Right? No. Now, this is B. This is B. You are just traveling from this point to this point. There is a current voltage dependent current source between B and C. But what do we know? We know A and C are equipotential. So can I just extend this line? And this is again B. So can I just extend this line? Yes, because they are equipotential. So yes, I can extend, which also means it is A. But for now, we are writing it to be C. So there is what? There is a current there is a voltage dependent current source between B and C. Please be very careful with the directions. The direction, please be very clear. Okay, so this is the direction you are provided with. Now, keep following. Between C and D, there is a 10 ohm resistor. See, C is right here. You extended C here, but D is not on the figure that we have drawn so far. C is not on the figure we have drawn so far. So we need to utilize our information that B and D are equipotential. So I just extended this and wrote a point D, because B and D are what? Equipotential. B and D are what? Equipotential. And there is a resistor of 10 ohms here. Yes, there is. Similarly, now extend point D again to a D. Right? But C and E are equipotential. C and E are equipotential. There is a current source between E and D. Please be sure with the directions. Between E and D, yes, there is a 25 ampere resistance. Between E and F, there is a 100 ohm resistor. See, if you do it yourself, you will find each and every step to be, because I've drawn it for you, it may, seem a little difficult to attempt. But I want you to pick up your pens, do this for yourself. Right? So you will understand how to draw equivalent circuits when you're provided with equipotential points. You need to understand it is a very basic topic, but it is the point where a lot of you will make mistakes. Right? Now, what is asked? What is asked by the question? I1, I2, I3 and I4. What is I1? I1 is the current between A and C. Between A and C. Can I mark this one to be I1? Right? What is I2? The current between B and D is I2. Direction this way. Direction would be this way. So can I write this to be I2? Right? Between C and D, rather C and E. Between C and E, we have I3. Direction again this way. Between D and F, direction this way. So you are asked with I1, I2, I3 and I4, right? Now tell me, looking at the network, what method would you prefer? See, why is KVL not suggested? Because how many times do you have to apply KVL? How many loop meshes do you see? 1, 2, 3, 4, 5, 6 meshes. So it is not advisable. What do you, but in general, tell me, this is all equipotential, this is all equipotential. How many nodes do you see? There are only 2 nodes in this network, right? So let me just ground this one. And this potential is already defined to be what? V1. So if I calculate V1, can I calculate the currents easily, much more easily? Right? I'll tell you how. I hope you're clear at till this point. So I'm taking this figure to the next slide. Now tell me. This I've grounded. This is the potential V1, right? Tell me at this point, okay? Tell me the currents that you're encountering. If this is node V1, if this is node V1, this is node V1, this is node V. Every point on this node will be what? V1. So how many branches are there? 1, 2, 3, 4, 5. Okay. So starting with the leftmost branch, can I write the current in the branch A to B? This is what the entire one is, node is V1, right? Can I write V1 upon 25, because higher potential minus lower potential divided by the resistance will give you what? Outgoing currents at this point, at this point, at this point. See, this is the same point. If you draw it like this or you draw it like this, if you would have drawn the figure like this, it would have meant the same, right? Because they are what? They're connected by conducting wires. So yes, it is the same thing. If I draw A and C like this, or if points this resistance, this resistance like this, or if I draw them like this, it is the same thing. I hope you're not getting confused at this point. Okay. So this is what? This is 0.2 V1. This is what? 0.2 V1, but it is not outgoing. It is incoming. It is incoming to the node. So how will I represent it as? I will represent it as minus. Because it is an incoming current, I will represent it as minus 2 V1. If 0.2 V1 current is going into this network, can I say minus 0.2 V1 is exiting the node? It's the same thing. It is all about the convention, right? Plus, can I write V1 divided by 10? Right? Plus, it is already outgoing, so I will directly write 25 plus V1 divided by 100 is equals to what? Sum of all outgoing currents at a given time on a node is equal to 0, right? Right? What I am doing, I am multiplying the entire equation by 100. Can I write 4 times V1 minus, if I am multiplying it by 100, it will be what? 20 V1 plus 10 V1 plus 2500 plus, I hope my handwriting is clear, plus V1 is equals to 0. I will try and work upon my writing though. So tell me what it makes. This is 5 plus 10 is 15 minus 20 is minus 5 V1 minus 5 V1 equals, I am sending this to the right hand side, it will be minus 2500, right? So can I write V1 to be what? 500 volts, right? So what we have done so far, we have calculated the value of V1 so far, and what it is calculated, it is found to be 500. What it is found to be? 500 volts, right? Now, still our question is not solved. Why? Because we were to find out what? Currents. Now, what can we calculate currents? So far we know that the potential here is 500. Can we calculate current in each branch? Can we calculate current in each branch? Tell me. If this one is 0.2 times V1 and V1 is 500 and V1 is what? 500, what would be the current in the branch B to C? 0.2 times V1, right? What is 0.2 times V1? What would that be? Can I write it to be 100 amperes? So this is what? 100 amperes, right? Now, please stay with me with this question, okay? This is what? 500 volts. This is 500 volts. The resistance here is what? 25. What will be the current here? What is the current here? Tell me. 500 divided by 25. So this is what? 20 amperes. Right? Right? Now tell me. Tell me. This is again. Let us just for now. Just let us calculate the currents in each branch. Okay. You have 500 here. This is 10 ohm resistor. This will be what? 50 amperes. It is already given to you. This is 25, so you don't have to worry. This is 5 amperes. So far you have what? You've done the calculations for each current. Right? Right? Now stay with me in this question. See, if this is 100, if this is 100, right? If this is 100 and this is 20, if this is 20, how much current would have? See, if this is 100 and this is 50, right? If this is 100 and this is 50, so if 100 is this and 20 comes out here, if there is 20 amperes current in this branch, 20 amperes current in this branch, right? So if there is 20 amperes, so what would have been here? So this 20, this is the highest branch, so this must have been supplying 20 here, right? So what should this be? This should be what? 20. This should be 20. So if this is 20, what should this be? 80, right? If this is 20, because 20 comes here, if it in this branch 20 is is being supplied, so 20 must have been flowing right here also. See, 20, it is open branch, no current here. It is open branch, no current here. 100 is going here, so it must have supplied this. So this should be what? 20 here, 80 here. If 20 is going here, this is an open branch. This should be again 20 amperes. So I1 was given to you in this direction, and what it turned out to be a 20 ampere current flows from C to A. But what we were asked, I1 is the current flowing from A to C. So can I clearly write I1 is equals to what? Minus 20 amperes. Right? Right? Now tell me. This is 20. This is 100. An 80 ampere current flows here. An 80 ampere current at point C. Please stay at point C. 80 ampere current flows here. 80 ampere current flows here, right? If 80 ampere current flows here, 50 divides to this point, then how much current should be flowing here? It should be what? 30 amperes. At this point, if 80 is incoming, it should be divided into two branches. So this is 50, this is 30, right? Right? Now this is 50. This is 50, right? And again come to this point. Coming to this point, if this is 25, so this should have been 5. Only then the current is flowing like this. So again, come at this point. This is again 5. So I4 is again 5, which was given to you. At this point, 25 plus 5, this is what? 30. At this point, if you come, 50 is coming here, 30 is coming here. So this should be what? 80. Right? So can you calculate the currents for yourself now? I2 was given in this direction. It is found that from D to B, the current is 80 amperes, but you were asked the current from B to D. So it should be minus 80 amperes. For I3, can I write it to be 30 amperes? And I4 is what? 5 amperes, right? Look at the figure and you will realize I4, yes, it is 5. I3, yes, it is 30. It is in the same direction. So this is the question that we did. The important concept was what? Equipotential points. So it is something that we have done in our childhood also. We know what are parallel points. It was a simple question on series and parallel, but it used your concepts of what? It used your concepts of nodal analysis. Right? It used your concepts of what? Used your concepts of dependent sources. Right? And also what it did was, asked the question also asked you to be very clear about KCL. So current division. Incoming current divides into two branches. Right? So revise this question for today. Revise well this question for today. Sit and do it by yourself. Note down the question for yourself. Do it for yourself. So if you keep, even if you do one question very clearly, it will help you a lot in your concepts. Okay. Tomorrow we'll take a class on voltage division. It's a very basic class again tomorrow on voltage division principle, and we'll do a lot on parallel on current division and such principles. I'll try and bring more PYQs for you tomorrow. Okay, so it will give you confidence that you can, these are the kind of questions that you can attempt. Okay, chalo, see you tomorrow everyone.